All right, good afternoon, everyone. Welcome to DPTrace, dual-purpose trace for exploration analysis of program crashes by Rodrigo, Branco, and Rohit, Mothe. I'm sorry, I butchered it. Before we begin, if you haven't had a chance to pick up your merchandise, today is your last chance at the Black Hat Swag and Bookstore, and they both close at 6 p.m. And please remember to put your cell phones on vibrate.
Thank you. Hello, everyone. I'm Rodrigo. This is Rohit. I'm really sorry for my really bad Brazilian accent, but I hope everybody can understand me. Thank you for your time and being here, and I hope we can have fun during the presentation. So just a very quick disclaimer, even though we work for Intel, we did this research in our research time and personal time. So it's nothing related to Intel, really. At Intel, we don't work in the Intel security group. We work with CPUs. So really, that's nothing to do with our work at Intel. So blame us for any mistakes we make, not the company. So a very quick agenda of what we're going to discuss here. We're definitely talking about crash analysis, right? We're talking about exploiting primitives and how you can find that and differentiate that in a given crash. So we will walk you through a lot of of the concepts that we use, and then finally we're going to do some demos of the tool that we're releasing. So everything here is basically open source. So just after the talk, it will be available in GitHub. Everybody can download, play. The crashes we're going to be using, it will be all available, so you can go and really do yourself, analyze, send feedbacks, and hopefully everybody will send commits to us as well. One important thing is there will be no 0 days presented here. So if you're expecting 0 days, that's not the talk, right? We're going to analyze old bugs to demonstrate that the tool capabilities and what they are. So the objective here is really to contribute to improving the state of the art in crash analysis. When we say that we're improving the state of the art, please don't misunderstand us. We are not saying we're doing a huge leap. It's not like we're solving the problem. We are far from that. It's a very small contribution, but it is a contribution moving forward in that area. We all know that there is a lot of things that are laborious, that are really handwork. And what we do is try to automate a part of that and really help an analyst or an exploit writer to analyze a crash. This is really something for helping and augmenting the analysis. We are not really doing anything that is fully automated that completely replace an analyst. That is really not our objective here. We will demonstrate that we're using hybrid techniques with backward taint analysis that are very instruction specific, that does taint propagation, and then we also use forward analysis that is more at the page level. So we will explain all the details during the talk, but just so everybody has an idea of the objectives here. We all know that the current state is really bad, right? We know there are buggy programs. We know there are more bugs being actually inserted in code than actually being fixed in code. So the state it's really hard. And triaging through crashes and triaging and prioritizing is a very hard task. So the exploit writers need to be sure that they're actually getting the best bugs that for writing the exploit. The MSRCs and component MSRC is the response center for Microsoft, but the response teams in different companies, the PCerts in different companies, they also need to triage the submissions they receive. Bug bounties need to triage the submissions. So everybody has a very similar problem of receiving potential crashes and defining if they are really a security vulnerability or just a potential bug in the software. So that's why we are here, right? So we know the problem. Of course, we also know that not necessarily what you see is what is inside, right? So be careful with the ponies over there, right? So when we're talking about taint analysis, really we just want to answer two fundamental questions regarding the crash differentiation, right? The very first question we're trying to help answer is really does the attacker has control over the faulting instruction, the instruction that actually generated the crash? So we want to know if anything related to that instruction is coming from the input that is under attacker control. And the other thing that we want to know is the forward execution, after the crash, knowing that the attacker controls the input, is the forward execution actually giving any primitive that is of the interest for the attacker? So essentially, if there is a good primitive, and that primitive is indeed controlled by the attacker, that means there is something that is advantageous. That doesn't mean that the exploit will be possible, because there is still mitigating factors that might influence that bug. But at least we know that the attacker has control over a primitive that is advantageous for him or her. So this is basically what we are here to try to do. One thing that is important is when we're looking for defining if the data is coming from the input of the attacker control, we do a very specific instruction by instruction tracing. So it's very detailed Taint analysis where we propagate Taint. When we do it forward, instead of doing instruction by instruction, we try to do in less level of detail so we can let the program go and see what happens. We're going to see how that plays on when we analyze the crashes. So a very quick history of the backwards Taint analysis. So the original motivation for that idea, the original sparking point of that idea was we worked together, me, Julio Alto, Balestra, and some other friends in a company. And basically, one of those friends of us, he came to us and he was doing a forensic analysis. He recovered some files in that forensics analysis, and the files were crashing a very important program. So it was at the time Microsoft Excel. And the file format at the time was not really open. So it was really hard to analyze those crashes and define, hey, are those crashes really security vulnerabilities or are they not? One of the reasons that it was hard, it's because the crash was not coming from a fuzzer, so we didn't really know which part of the file was generating the crash. So that's how the idea actually all started. And this idea was developed along the years in many different projects, either trying to integrate with fuzzers, trying to do the analysis in Unix environments, and with the analysis in Windows environment, led by Julio Alto, who is also here in the presentation. So basically, that's the history for this backwards Taint. When we go for the forward Taint,
yeah, so originally the motivation to do the forward Taint was when you're running a bug bounty program and you have many submissions that you need to bang out really quickly. Some of them are immediately exploitable. You can see that either the analysis is really good, but for many others, you're not able to tell if they're really exploitable or not. So that was kind of our original motivations to do the forward analysis approach. Also, if you have a huge corpus of fuzzing crashes, you can do rudimentary bang exploitable categorizing, which will tell you which one, and it'll just bucket them into read access violations or write access violations. The one that you know are exploitable, you're good to go, but as it often happens, there are a whole bunch of read access violations that you're not sure, and then you have to spend time to analyze for each of the crash. What we noticed that while doing that for some specific classes of bugs, it's a manual process with lots of steps. Some of those steps we felt could be automated. Of course, I'd like to mention at this point, when we say automated, it's not just a magical solution of you run it and it tells you that. Some of the tools actually try to do that. We don't. We try to go for a more practical approach where it has to be supplemented by manual analysis, but we do try to automate certain aspects of that. In a sense, you can view this as prototyping exploitation. So at the time of crash, you kind of mimic object control and see that so there are two parts of the problem, as Rodrigo talked about, the backward Taint. Through the backward Taint, we try to answer the first part of the question, which is, do you have control? And second, well, if you do have control, can you go forward and find an exploitable primitive after that? And we thought this prototyping exploitation or this mimicking exploitation is an easier problem to automate rather than just a one-click solution where you say, oh, click and just write me a final exploit. So we felt that's a much more difficult problem. So of course, there are existing solutions. I also want to highlight that we're not trying to be them. We're not trying to beat them. Ours is a different approach. But it's good to know what other solutions are there, what approaches they take. There's Bang Exploitable, obviously, the classic tool. Helps you quickly categorize crashes, gives you some contextual information. Everybody knows that. Well, hopefully we do better than Bang Exploitable, if not any others. There's SpiderPig. It's not available for testing, last we checked, but there's a really good paper. It's a pretty advanced tool. There's Taintbox. Taintcheck, it's based on dynamic RO Valgrind, and it tracks the propagation. It's used to detect overflow conditions. Does not really give you a lot of information to help you in the process of exploit creation. but it's a good tool also. There's BitBlaze, which is a really good platform for binary analysis. It provides a much better classification of exploitability than the much simpler bang exploitable. And recently we were made aware of Mothe framework by Cisco Talos. It's built on CMU's binary analysis platform framework. I think the code is publicly available, and I would recommend you check out. It's a really awesome tool. It's a very advanced tool. They also have a backward taint analyzer, of course, using different principles. And for forward execution, they primarily use symbolic execution. So they just sit there and try to evaluate through symbolic execution, and they try to look for exploitable conditions right after the initial crash. We follow a different approach, which I will detail. I think each of the approach has its own pros and cons. But anyway, do check out Mothe. It's a good tool also. And yeah, Rodrigo will talk about the specific state transition of memory corruption.
So yeah, when we look into memory corruption and many different classes of vulnerabilities, in the end, you don't really have like a direct relation between, hey, like the crash happened, and that means like the previous instruction or the immediate instruction is really the offending instruction. Like many classes of vulnerabilities, like in heap overflows, you might end up corrupting something that actually crashes much later. So it's not that simple, that trivial to define, hey, is that condition under control, and is that condition like really giving an attacker a primitive? So we just wanted to make sure that everybody understands that complexity. And that's why we're not trying to fully automate, but we really need an analyst behind it to do the analysis, as we will demonstrate during like the flow. If you consider like the taint propagation, which is really the way that we use like for the backwards analysis, you really have like a transition, like a relation between instructions. So imagine that you have a given area in memory that the analyst defines, hey, this given memory in the area is controlled by the attacker. Either because it does have like the attacker input, which might be, for example, a file or a network packet, or something that the analyst, through his analysis, understands it's under influence of the attacker. From there on, we can basically define if all the instructions that are actually accessing this memory area basically are propagating the taint. So like if, for example, you have an instruction at the location A, and then the memory area in location A that you know is controlled by the attacker is moved to a register. Now you know that you also control that register. So because we can have that transition relation between, hey, if you have tainted area A, and A is used to derive somehow B, and now we have like a tainted area B, if B is now used to actually derive C, we know that C is also under control, and we have this indirect relation between A and C. So that's actually what we need to understand if in a given moment of like the execution flow of the program, it's that the data deriving from the input of the attacker. So that's how we use it. There are a lot of like challenges in doing that, right? One of the challenges is really like how do you really avoid like state explosion, right? And how do you really like mimic all the instructions being executed in a flow? We will make it clear that one of the limitations that we have is when we look into a flow, there are flows in a program that can be implicit. So for example, in this case, even if the attacker controls X, meaning that Y would receive actually 0 in this example, right? We don't really follow what like conditions that did not happen in our trace. So we are blinded to that. So one of the samples that we're going to demonstrate in the analysis 3, there are like many of those cases. The exploitable condition is actually not on the original trace. So that's why you also need the analyst for our approach, because the analyst can force those constraints. He can know that the constraint is also coming from the input. Therefore, the attacker do control that constraint, and he can force a new trace through the correct path that actually is the path that he's interested of. So there is a lot of manual analysis, and we're going to demonstrate one of the analyses that has lots of those constraints. So in the backward taints, as I mentioned, like just starting like clarifying a little bit how the approach works, we basically divided the process in 2 parts. We do a tracing, which is getting the program, executing the program, and really like single-stepping that execution from the program. We're gonna show like some of the numbers that like we had like in the analysis that we made, but we managed to trace, for example, 10 million instructions in Adobe. We managed to trace like 800,000 instructions in Internet Explorer. So it is slow because we're single-stepping, and we already have some ideas for optimizing that, avoiding some certain modules, emulating certain flows. But right now, that's the way that the tool is implemented. And then we have like an analysis part, which is responsible for really looking and doing the taint analysis of the generated trace, which we called verification step.
So with the forward taint analysis, the idea is, as I mentioned, to see what primitives are available which can be exploited later. And as I mentioned, we were trying to prototype input control. And the way we do it, instead of symbolic execution like how Moflow does and some other tools, what we do is we try to satisfy the constraints that cause the access violation, try to fulfill them, redefine references, and then continue. Essentially, we allocate, at the time of the crash or the exception, we allocate a fake object structure in memory. The initial property of any such object structure in memory should guarantee to, well, at least a reasonable extent, that all the memory references within that should be resolved and should not lead to a crash immediately after. So any virtual function tables, object pointers, any sorts of data, all the pointer references can be resolved. And the way we allocate it is if it's any additive or subtractive reference, it still falls into a domain which points into our control object. So in essence, you could imagine this like if it's a use after free bug. So basically from within the debugger, let's say like for a use after free, you would abuse LFH, reallocate the freed object via JavaScript or whatever and do that. But from within the debugger, we kind of try to do this all for you. And the analyst can just redefine the references to move forward. Apart from use after freeze, if you think of some out-of-bounds access violation crashes, it's the same idea. Like if there's an object and the initial crash was trying to access something beyond that, ideally through the exploit chain, you would do that via JavaScript or within the browser, wherever you're doing it. But within the debugger, we give you an object right after that. So you kind of mimic initial control, and then you carry forward to see if there are any exploitable primitives. This is just one simple example of how the memory structure is laid out. Basically, each dword within our fake object is basically a pointer to the corresponding object, and we have a whole bunch of objects in chain. The last object has a bunch of junk values. In this particular case, we gave page read-only memory permissions for each object. You can tailor this based on initial analysis if you want to change the permissions. The last object is like a guard page, so any access should break. And the idea is once we do that, we take the root of this chain of objects. It's kind of like a linked list of, and we take the root and redefine the references at the time of the exception. Implementation details. So when we tried to implement this approach, we chose WinDebug. We play straight with the debug interfaces within WinDebug. That's our debugger of choice, and also Windows is our platform of choice. We thought it would be very helpful since our initial motivation for this approach was to have a practical solution that people can use straight up. So instead of bang exploitable, you could use this in your analysis. We chose WinDebug, but in essence, the principle could be carried out to other systems as well and other debuggers, hopefully. Also, the trace file that we generate during each backward trace, it contains the mnemonic of the instruction, the operands, all the dependencies of the source operand. And we essentially create a tree of the entire data flow from the initial program crash to wherever we go forward after that. There is an analyzer portion. There is a GUI and a command line analyzer for this. We made a command line analyzer within the debugger for quicker integration. You can script against it and see the results. But there's also the GUI in case you want to specifically look at one case and analyze it. It helps. But we do have a command line program if you want to just automate a bunch of sequential modules that you want to use from our tool. And it basically searches the tree, the analyzer, using a BFS algorithm. And as I mentioned, the forward stepping basically uses the Win32 functions. It uses virtual alloc x from within the debugger to the debuggy process to allocate the fake memory structures, uses virtual protect. And you can tailor them to have whatever memory permissions you need. At this point, yes, I have to say a picture is worth 1,000 words, or 42 words in this case, because if none of that made sense, hopefully the next flow diagram will. So this is kind of like how our flow would look like. We would start the program, then we'd have an initial crash. And if you see to the left side, those are the three things we're going to be doing at every exception going forward from there. So crash, move forward, another crash or exception. So we treat each of them equivalently, and we do these three things towards the left, as you can see. We check the backward trace, make sure that there is taint propagation, make sure that there is either very direct or some form of indirect control, and we can influence that. Then we reallocate that whole fake object structure, redefine the references, and then move forward. And hopefully go to another exception. It'll have one of the constraints, do the same thing, get the trace, make sure we have taint propagation, reallocate the fake objects, again, redefine references, move forward, and we keep going forward. Hopefully, we reach a point where we find an exploitable primitive, and at which case, we don't have to do all the three. We just check the backward trace, then check the taint to make sure it's still controllable in some fashion. And if it's exploitable, if it's an exploitable primitive, that's good for us, and we're done. If not, well, we keep going down this path, and yes, there'd be a whole lot of state explosion, and well, go down to hell. So that's kind of how it looks like within the debugger. You load DPTrace, the plugin within Windows Debugger. That's the help screen, and it lists some of the other sub-modules within the plugin that we have. We have DPTrace trace, that's a tracer, as you see in the second file, second screenshot, sorry. You say DPTrace trace, and you give the path to the log file, and it'll write to disk. There is the DPTrace forward, which helps you allocate a number of objects, size of each object, and the specific permissions you want to pass it to it. By default, it'll also allocate, I think, 2 objects, but it's also given in the help screen. And there is the analyzer. This is the command line analyzer that we were talking about. You could just do DPTrace analyzer. But in some of the screenshots we'll see in the demos, we try to show you the GUI of the analyzer only because it's easier to visualize. But just so you know, we have it right in the debugger. So if you want to script against it, you can easily do that. Let's move on to analysis on some dead bugs. And that's a Game of Thrones reference for those of you who got it.
Excellent. So one point, before we starting, showing those analysis. So together with this presentation, we also releasing a paper, okay, that actually has details on that analysis and all the screenshots. The screenshots are not going to be super visible, probably. Some of them are, some of them maybe not. So don't worry about that. All that will be also in the paper, with the explanation. The idea here is more to demonstrate the process and how we actually use it in 3 different bugs. So we start from a very simple one, which is a classical Stack Overflow, and then we go to more tricky ones. The intention is to demonstrate that you can really use that process from the simplest of the issues that you can just immediately notice that it's exploitable condition to the more complex bugs where you really need to do a lot of manual analysis and a lot of constraints change during the analysis that you're doing. So the very first bug is an Adobe Reader bug from 2010. So probably everybody remembers that bug as a libtiff bug. So when you have an image file embedded in a PDF, the libtiff TIFF has its own header. In that header, you have IFD entries. In the IFD entries, you have a tag type. So for 4 different of those tag types, what the library was doing was basically getting another value from the header and using that as the size of the element to be copied to a fixed size buffer, leading basically to a classical Stack Overflow in this case. So that was a very trivial issue. And it's actually interesting because that already shows for the initial motivation when the tool started being developed, right, was really to look into this file format bugs and be able to analyze those. So that's why we chose it. In this specific case, when we started, from the moment that we had the create file to the moment that we hit the crash, we had 10 million instructions. So it took 5 hours to really trace that in a 1 gig VM running. So it's not really a good, right? So you can cheat as an analyst and you can actually put your breakpoints closer to where the problem is happening, right? So since you already seen there is a crash, you are seeing the location of the crash, and you know where are the data, so you can try to put your tracing to be a little bit closer to the location of the crash so you avoid doing that much tracing. As I mentioned, one of the ideas for the future is really optimizing this tracing, excluding certain modules, doing some other smarter tracing. But right now that's a limitation, so we kind of cheat a little bit to actually get closer. So if we look into the analyzer and we look into the instruction that is actually the faulting instruction, we can clearly see that there is a taint value coming from the pointer that is being dereferenced. Therefore, we know that we can make that dereference to actually be something of value, right, for the attacker. So we know that's happening. And basically, with that taint information, we can actually look further and for example, in this case, in the GUI, and really see the instruction that actually the flow is flowing through, to see, hey, where's the previous instruction where I actually have control over that's also coming from the input. And then you can do that until you actually find out where really is your controlled data. So in this case, we knew that we do control the pointer, so we can easily make that pointer point to somewhere we want, so in this case, 41, 41, 41, and therefore we can really look into the flow. And finally make that coming from our file to actually overwrite the EAP, and in this case, we can control the execution flow of this program. So this program is very simple. It's clearly exploitable, right? As we can demonstrate. So the next examples are much more elaborate with the idea of showing something that just the backward Taint cannot tell you. You really need to go forward and do more and really look into the constraints. That's why we included these other examples to show you that just the backward analysis is not enough. We needed something more than that.
Yeah, so for the second analysis, we look at an IE bug. It's CVE 2014-0282. It was reported by Simon Zuckerbrand, if I remember correctly, from ZDI. It's a C input object use after free, and it was patched actually a few months before Microsoft released the so-called silent mitigations, the memory protection feature, isolated heap, etc., which is the reason if you try this POC on an older version of IE, you don't need to change any settings. It will crash right here instead of a null pointer dereference, which you see with modern POCs, because by default, memory protection feature is enabled, and then the heap manager doesn't actually free.
Yeah, we're going to include all those crash files together in the repository, just to make it easier for everybody if you want to just.
And also, I think there are a bunch of places you can find the trigger for this. A couple of months ago, I think NCC Group and some other person, I don't remember, released an actual exploit for this, which pops calc. It was done on Windows XP, SP3, but we looked at it, and it can easily be at least ported to Windows 7, IE 11 on the vulnerable version. You'd run into a bunch of more problems on Windows 8 and later versions, but it can be done. But yeah, there are actual exploits for this. So we do know it's exploitable, but then we want to show you how you would analyze this if you were an analyst and you get this crash, which innocuously looks like just a read access violation because it's taking the stale reference that is ESI here is pointing to a freed object. So what we do here, if you can see that on the screen, is we do DPTrace forward. We allocate 2 objects of size 68. That's very specific to this version of the IE that we were running on Windows 7. In the next example, we'll tell you that you don't have to be precise with the object size, because the way DPTrace forward does a virtual alloc call, it uses virtual alloc internally. It allocates 1 KB of a page. So even if you roughly say 100, 200 bytes, if there's any access after that, you still control that and it will fault. So you can start with a rough guess and then change it later. So what we do at the time of initial crash, because right now it probably doesn't look exploitable, right? It's just a read access violation. What we do is we did DPTrace forward. We allocated 2 fake objects with 68 bytes. Then we redefine the references. In this case, we just redefine ESI to point to our fake object. And then we basically start the tracer. The tracer itself will inherently start the stepping, and it will start tracing each instruction. By default, as of course Rodrigo mentioned, we trace each and every instruction. So it's not just within MSHTML. It goes all the way down to NTDLL or whatever, which is why it takes a bit some time. But if you're confident, there's a very easy way you can change that within the code and only track certain modules. That's also something we plan to do in the future. So you start the tracer right here, specify the path to the log file. And a few instructions later, it just crashes again, and there's another exception. So what you try to see is, do you control this exception, and is it exploitable here, or do we need to keep going forward? Again, as I mentioned, we show the GUI portion just because it's clear. All of this can be done from the command line. I think there's a screenshot later that shows this. So you don't have to open the GUI, right-click, add the ranges. It's not that manual. It's kind of automated in the command line. But again, we just show it here so you can visualize it better. So that's the allocated range of our fake object structure in memory. You can even add multiple taint ranges. This is just 2 objects, so I add the start of the first object and the ending of the second object. I add the taint range, and that's an easy way for you to see. It's not super clear, but the visual data tracer at the back has the whole tree of each instruction that we started tracing from the initial crash to this next crash. And you can easily check if you control if the taint propagated and if we control anything in this exception. And clearly, as you can see, the EIP control is at CCC. We can make sure to check the trace again, make sure that it comes from our fake object and it's just not some random value somewhere. So I just dumped ESI just to show you, because initially that was the vulnerable reference that we redefined before continuing the forward execution. And you can see that the first object points to the second object, and the second object, if you remember, the block diagram was just a bunch of junk values meant to crash. And that CCC is essentially coming from there. You can also see it in the visual tracer, which is the GUI of the analyzer. It's basically a call EDX, and EDX, like a couple of instructions above that, was derived from the tainted value, which was initially pointed to by ESI. And that's the analyzer. When you just right-click and say check taint, it'll give you the flow of how you reach that taint and how your freed object, your fake object essentially caused that exception. You can follow the path. And as I mentioned down below, you can do the same thing by bang DPTrace analyzer, specifying the trace file, a bunch of other flags that you can look at the help, and it'll give you the same contextual information instead of you having to open the GUI and do all that. So one thing that Rodrigo mentioned was, if you noticed, we basically started from the crash point and moved forward, but we didn't do any real backward tracing, in the sense that when we attached the debugger to the instance to IE11, then the debugger breaks, and then from that point of program startup to the crash, we didn't show that, right? And the reason is, you can see that it's about 677,000 instructions. Then it stops before it passes control to IE. IE gets spawned, and then that's another 891,000 instructions. It took a while, probably close to 30 minutes, I guess. And this was a VM with 4 GB RAM, I think. But the thing is, if you really wanted to do that, you have all that contextual information. You don't really need to. This is where you see the play of how this would benefit you if you already knew kind of what you were doing. And if you were a skilled analyst, you wouldn't start tracing right from the start of the breakpoint, the initial breakpoint before program startup in WinDebug. You would maybe put a breakpoint somewhere before the initial crash occurs. And the closer you can do that, of course, it needs a little bit more analysis, but the trade-off is that the closer you do that, the smaller your log file is going to be, and you can do it faster. And as I was mentioning, that's too much information. I don't think you can read that. But instead of the whole visual analyzer and you trying to do that, it's just a bunch of commands from the debugger, and it'll take the trace file that was dumped, specify the instruction indexes, and it'll check for taint of each of the instructions that led to the next crash. So it can be done easily from the command line. We integrated that too. Let's move on to a more recent example, which is CV 2015 6152. This was patched, I think, December 2015. Was reported by Blue Forest Security. I think it was Moritz Jode. I don't know if I'm pronouncing his name right, but he put the initial POC on Exploitability. It's categorized as a DOS exploit. Microsoft, when they patched, they said it allows code execution. But I have rarely seen Microsoft say that any use after free is just a DOS. They always say that. So you can either trust Microsoft, which you can, that's fine, or you can just analyze it yourself if you wanted to actually cook up an exploit for that. So we'll try to analyze. As far as I know, there's really no public analysis available, but if you want the initial trigger that works on this vulnerable version of IE, it's on Exploitability. It was put a couple of months ago, I think. But yeah, to the best of my knowledge, there's no exploit or there's no public public analysis of this issue. So it's a C object element used after free. One thing to mention is obviously this has memory protection features enabled. But the reason you see the crash there is because when we were doing the analysis, we disabled the memory protection feature from the registry. So if you're actually trying to exploit this, keep in mind you'd still need a bypass for the memory protection features. But this is just done for the analysis. So as I was saying here earlier, that you can do DPTrace forward with a very rough size. So we do deep trace forward, allocate 4 objects. We're really not sure how many references we bump into. And we say the size of object is 200. It's actually not 200, but as I was saying, you can just roughly guess and then move forward. You have 1 KB of kind of slack space to work with. 0x02, that's page read only. We just try with that, and then if something changes, we can dynamically reallocate and change some constraints. And it shows you the allocated ranges of the fake object. That's just showing you the fake object chain. Of course, as you see, it's a test word pointer EAX plus 24. It's trying to read 24 bytes into the free object, which innocuously looks like a read access violation. You're not sure if you can get exploitable primitive. So at this point, because we have our fake structure in memory, we just redefine the references to EAX, and we continue the exception with DPTrace trace and give the log file, the trace file path. Again, this is the GUI. You add 10 ranges like this. You can do it from the command line, same stuff. And basically, we keep hitting exceptions, and we keep checking if we control the taint at every exception. As we move forward, so one of the constraints here was, as we saw at the initial crash point, it's reading 24 bytes within the freed object, and it's checking for a constant value. So we will try to not meet that constraint. We'll treat that as data, but it's checking for 30000. We just do 300, just to make sure it's data, but we don't actually meet the constraint. So we'll follow up an entirely different code path than what we would have if we had met this constraint and hopefully some other constraint. So let's just try not to meet the constraint, and we continue the execution and try to trace it. And we end up in a bunch of more exceptions. At every point, we do the same thing. Make sure to check the taint propagation, make sure we have control, and then keep following execution. This particular execution, it doesn't tell us much, and we aren't sure of an exploitable primitive yet. So what we try to do is carry on another execution. And this is kind of the limitation, as you can obviously see with symbolic execution. You get much more tries. But with us, with our approach, you have to be kind of smart and work around. Otherwise, you lose an execution, and you kind of start from the beginning. So this time, we just do a rudimentary analysis of a few instructions here and there, not dig too deep. But then we try to meet some initial constraints that we see, so we can originally go down that path that we missed and see if that works. So we do the same thing. We do deep trace forward, allocate 4 objects again, 200. And as you can see in the left part of the screenshot, we try to meet a bunch of constraints. So we see that EDI is a reference, which EDI is holding a stale reference. We try to redefine that. There is a pointer on the stack that holds the reference. We try to redefine that. And we try to 24 bytes within the free object. It checks for 40000, that value. So we try to hit that code path. And then we continue the execution. And immediately you see that in that particular code path, we hit a much more interesting exception, which is a stack buffer overrun. The tracer tells you that it logged 3,664 instructions, and they were dumped to the log file that you had initially specified. And if you just do a preliminary analysis of what caused that and you check the stack, you see that it was because of a failed VT guard check. So that seems more interesting because it seems like we have some exploitable primitive, and hopefully there'll be a call after that VT guard check. I put an IDA screenshot primarily because you can check this even in WinDebug or our command line tracer or the GUI, but the way the basic block is arranged is in linear disassembly. It's very difficult to view that. So you wouldn't actually kind of get an idea of what's happening. But as you can see here, clearly, there are a bunch of other constraints. You have to bypass VT guard check, which if you had an info leak in MS-HTML, you could probably do that. Then there are a bunch of other constraints where it's comparing some offsets, but we don't have to worry about it, because if you see the red path in IDA in the graph view, it's going to another path. We don't want to go there. We want to go to the bottom basic block where there's code execution. And for those of you who are paying attention, of course, there's a guard check I call F pointer. So there's control flow guard to bypass also. But in principle, if you could So there's memory protection, VT guard, CFG, but in principle there is code execution, but with the constraint that you need leaks and bypasses for some of these mitigations. And at this point, we do the same thing. We confirm taint control. We see that we directly control this point. You can do it both from the command line and the analyzer GUI. And so obviously, looking at that, immediately some limitations that you can see are if a particular execution you kind of mess up, you kind of have to start from the beginning. And as you saw, we did a bunch of changes that were manual. So as we kept saying from the start, we do require a skilled analyst to know what he's doing, and it's not just like a one-click solution. But it kind of supplements most of your analysis, and you don't have to go poking around in IDA like 4 or 5 functions down to just see if you can hit an exploitable primitive. And yeah, Rodrigo will talk about specific challenges with our approach and what we plan to do in the future.
So yeah, definitely, as demonstrated, there is a lot of steps that still require manual analysis. The idea here is really augment that manual analysis, giving you some things that are automated during that manual analysis. Some of the challenges that were like very clear when we look in there is like, yeah, how do you know what are the ranges that have actually input from the attacker? So yeah, that in some cases will be very easy. Some other cases will be very hard. Like if you look into like even like a file format bug, those programs are very complex. So they start like copying the data and mapping the file in different locations in memory. And indeed, you will need to go and start like looking to all of those ranges. That's still like something that requires like some manual analysis. There is like a big challenges there on the partial training where like in some cases the Taint analysis can give you false positives because like you don't really fully control a value, but you somehow have some control over that value, and we assuming you control the entire value. So you can have like some corner cases there where you're missing something that you believe you have control, but you actually don't. Also, as demonstrated, right, like if there is mitigation mechanism in place, we basically telling you there is like exploiting primitives in that program, but we don't really help you towards like the mitigation mechanism, how you actually look into those mitigation mechanisms, right? So if you are an exploit writer really wanting to write the final exploit, you still need to be aware of those, right? The tracer itself has like some limitations on what we are able to trace. As I explained, because it's like very detailed like Taint analysis on the instruction set, we right now only support like really basic x86. We already actually formalized like the other instructions, but we still didn't implement it. So keep in mind if you look into some binary that you use like MMX or like a x87, that we are not going to be able to see that. So the tracer is blinded to that. Another limitation is really like this conditional code paths. As we saw, like you need to force the code paths of interest to happen if they are not happening in the crash file that you do have. So it really definitely have like a lot of manual analysis. And really, that's not magic solution. It's just, as I said, a small step forward towards doing something better. If we look into the future, other than like removing some of those limitations, trying to speed up the tracer, adding more instruction support, we have like a to-do file that we're really glad if anybody look around and start sending us comments. And the latest version and everything is available on GitHub, like on Black Hat 2016 repository. And just before we finish, I really want to say that we really appreciate the work done by Julio Alto and Dave, actually. If it was not for these two guys, this project was never actually going to be possible. Lots of that code is based on things developed by them. They should be speakers with us, actually, but since they didn't reveal the talk, we just didn't include their names as speakers, but they should have been here with us. So thank you very much, guys. I know that Julio is here. I don't know if Dave is here, but he was here.
If you're here, just raise your hand.
Yeah, so he's not, but he's probably drunk, which is really good for him. So I wish we can all go and get drunk now. Like if you guys have questions, we are here.
Yeah. Thank you.
We have 5 minutes, right? So we have 5 minutes. Any questions?
So very nice work. So I have 2 questions. First, what's the performance overhead? Because I think Intel has some hardware features called Intel PT. So maybe I don't know what's the overhead of this work. So the second one is, how can you find the root cause of some vulnerabilities? Because someone like integer overflow, and that leads to the memory corruption. and the 2 points are very far away. How could you locate the one like maybe a long way before? Yeah, thank you.
So yeah, we are definitely aware of the Intel tracing capability. We didn't use it just because in the tracing process we already actually help like providing information to what the instruction is actually doing. So that makes the analyzer easier. So tracing is a little bit heavier, but then analysis themselves are like much easier. So that's one of the reasons we didn't use it. Now regarding finding the root cause, yeah, there will be vulnerabilities that this approach is kind of dubious, right? You're probably gonna see that there is coming from a code path that is basically related to that. So you can see you still have control into that integer overflow into that arithmetic instruction that happened. So yeah, that approach would help, but not too much, right?
Yeah, again, you would specifically need to break somewhere before, like let's say it's a user for free, before the alloc happens and like the initial free happens and then the realloc happens. So yeah, there would be supplementary analysis to go with that. This would help you in terms of being able to trace dynamically and you can see whether you hit that or not. But yeah, it's not going to tell you the root cause of all the bugs unless you do have an idea of where to start and
a lot
basically,
of manual analysis.
Yeah, and basically do the whole chain of exception, taint, trace, exception, taint, trace. But yeah, that's a valid point.
Thank you.
Thanks.
Do you have any analysis when you compare your tool, the improvements that your tool is adding with respect to Bang Exploitable or any other similar tools? Or?
Well, obviously, Bang Exploitable would just give you the initial basic contextual information and categorize it. If you're talking about specific metrics, no. But as we saw in the analysis, if you had just stopped at Bang Exploitable, at least 2 of the cases, you would just discard them as non-exploitable and move on. So we at least try to do better than that. We don't have specific metrics with other tools. As we mentioned in our existing solution, there are a bunch of tools which use very different approaches. We just try to be very practical, and it has worked. But if you're asking specific numbers, no, we didn't.
Very likely, if you go for an approach like using this tool that we're providing, you will still use something similar to Bang Exploitable to actually at least group the crashes.
For the initial categorization, Bang Exploitable is the way to go. I mean, I'm not saying never use that. That's good. But then once you start trying to track which ones you would spend more time to focus on seeing if they're exploitable, you would use tools like ours or MoFlow or a bunch of other tools. But yeah, no, sorry, we don't have specific numbers. We didn't benchmark. But again, there is performance overhead if you don't know what you're doing and you end up tracing 10 million instructions. So
that's it. Thank you very much. We're going to be around. So
yeah, we'll stick around. Thank you.